So let's start off with some sample diploma questions. So a positively charged object is brought near to, but does not touch one end of a neutral metal rod on an insulated stand. The opposite end of the metal rod is grounded. The ground is removed, and then the positively charged is removed. As a result, so with this question, you got to draw out what's happening. So let's draw out what is happening. So a positively charged object is brought near to, but does not touch one end of a neutral metal rod. So you have a positively charged object, comes close to, but does not touch a neutral metal rod. The opposite end of the metal rod is grounded. Right? So what's going to happen is, if this is positive, these electrons are going to want to be by the positive, and electrons from the ground are going to want to come up and be inside of this. Okay. So the opposite end of the metal rod is grounded. The ground is removed, so we remove the ground. And then the positively charged object is removed. So the positively charged object is brought away. So what are we left with? Well, we're left with a negatively charged object. So D is going to be the answer. Okay, a student has three identical spheres, K, L, and M, on insulated stands. The spheres are those charges. So the spheres are touched, then separated without grounding in the following order. Okay, so let's draw out what's happening here as well. So we have K, L, and M. So it says that K is +3, L is -5, and M is +2. So the order, so these two are touched together. So what we would do is we would add that together and divide it by 2. That's how we get the charge. So this would be -2 divided by 2, so it would be -1. And if you're doing this right, all the charges, the total number of charges stay the same. So +3 +2 and -5 is equal to 0. -1, -1, and +2 is equal to 0, so that's good. And then the next step, K and M are touched together. So we're going to add -1 plus +2 divided by 2. So that's going to be +1 divided by 2, so +0.5. And this one stays the same. And then we do L and M together. So -1 plus 0.5 divided by 2. So that's -0.5 divided by 2. So that's going to be, oops, I'm running out of room here. So -0.5 divided by 2 is going to be -0.25, -0.25, and then +0.5. And we can see these all add together, and they end up making 0 in each situation. Okay, so 0.25, 0.25, and this one stays the same. So it looks like that answer is D. D is our correct answer. Okay, and which of the following diagrams best shows the leads of the electroscope that are touched with the metal rods? So it says that a student touched electroscope 1 with a metal rod. So it looks like they're charged up already. So if I touch this with a metal rod, right, any extra charge in here is going to go into my metal rod. So these ones will become straight like that. And then the student touches metal 2 with a glass rod. So because the glass rod is an insulator, the extra electrons won't be able to go in there, so it's going to stay charged. So it looks like B is going to be our answer. Okay, so let's do Coulombs law. So curriculum things you need to know. Explain qualitatively the principle pertinent to Coulomb's torsion balance experiment. So you need to know about Coulomb's torsion balance experiment. Apply Coulomb's law quantitatively to analyze interaction between 2 points. Determine quantitatively with numbers the magnitude direction of electric force on a point charge due to 2 or more other point charges in a plane. Compare qualitatively and quantitatively the inverse relationship. So we got to compare Newton's universal law of gravitation with Coulomb's law, and use free body diagrams to describe electrostatic forces acting on a charge. So before we start, I want to point out a couple things in the data booklet. So these are common particles that you need to know. So there's an alpha particle, which has 2e, negative 1e, and then a proton is positive 1e, and then we have a neutron. So this E refers to this elementary charge. So an alpha particle would have times 2. So this would be 3.2 times 10 to the negative 19. This would be negative 1.6 times 10 to the negative 19. This would be positive 1.6 times 10 to the negative 19. So you need to know these common particles. They'll come up in questions. You have to be aware of them. So Coulomb's law describes forces between 2 charged objects. So our electric or electrostatic force is equal to K, Q1, Q2, all over R squared, where Fe is our electrostatic force. It's a force, so it's in newtons. K is a new constant. It's Coulomb's constant, which is 8.99 times 10 to the 9. And that can be found right here in our data book. Q1 is charge in coulombs. And distance separating 2 objects is in meters. And what does this formula kind of remind me of? Well, it reminds me of Fg equals G m1 m2 all over R squared. That's what it reminds me of, right? It looks almost identical. So you need to be aware of the Cavendish experiment. So Cavendish was able to verify a direct relationship between gravitational force and mass 1 and mass 2, and an inverse relationship between gravitational force and distance. So when mass 1, mass 2, and R squared were all graphed against Fg, the slope of the straight line gave us the gravitational constant. So this is Cavendish's experiment. So let's open this. And we'll take a look. So this is the same as the Cavendish experiment that confirmed Newton's universal law of gravitation, right, where you have 2 masses. You have this laser pointer here, and here's a mirror, and then here's a scale that shows degrees. So this rope right here is a special type of rope. It's called a torsion rope, and it's calibrated so that if it twists a certain number of degrees, it corresponds to a force. So if we play this again, right, we get them close to each other, they attract each other, it twists this torsion fiber, and then we can get a reading for the force that they exert on each other. So this was the Cavendish experiment. And the Cavendish experiment was for, oops, I don't know what's going on here with this. The Cavendish experiment was for Newton's universal law of gravitation. Let me put that in there. There we go. And Fg and M1 have a nice direct relationship. I guess that was in there from before. M2 had a direct relationship. These guys had an inverse squared relationship. But when we took our R values and we squared it and put M1 and M2 up here, we always got the same slope. Our slope is 6.67 times 10 to the negative 11, right? And that became the constant, right? That became with our y equals mx. Our y value is Fg. Our x value is all of this. And then our slope became our g value, right? So they got this constant from doing that. So Coulomb's Cavendish experiment was super similar. He did the same thing, but instead of masses, he did charges. He measured Fe while varying Q1, Q2, and R between them. He was able to vary the charge by touching it to a second equal-sized ball and reducing the charge by half. So what were our manipulated, controlled, and responding variables? Well, let's take a look at that. So if we take a look at our manipulated, responding, and controlled variables, well, you need to do 3 separate experiments. So experiment 1, experiment 2, experiment 3. So he wanted to find out, did charge 1 affect it? Charge 2, did that affect it? And then the distance between them, right? So his responding variable, oops. So this was our manipulated, and our responding variable would always be the twist of rope. Same idea, which corresponded to an electrostatic force. So the twist, or Fe, the twist, or Fe. Okay. And then our controlled variables. Well, we know that each one of these affects the experiment. So if we're manipulating Q1, we want to keep Q2 and R the same. If we're manipulating Q2, we want to keep Q1 and R the same. And if we're manipulating R, we want to keep Q1 and Q2 the same. So we got to control that. So when he did that experiment, when he manipulated Q1, kept the other ones controlled, he found a direct relationship. Right? Same with this, he found a direct relationship. He found an inverse relationship when he did R, but if he graphed 1 over R squared, then he got that nice straight line. He found that they had an inverse squared relationship. And then when he stuck all of them together, he found that the slope, no matter what the charges were, was always 8.99 times 10 to the 9, which told him that was probably a constant. So let's do an example. A pith ball was charged by friction to 6 microcoulombs. It was brought into contact with the second uncharged pith ball, then separated. The second pith ball was got into contact with the third uncharged pith ball, then separated. When the first and third pith balls were brought within 5 centimeters of each other, what is the electric force between them? Okay, so let's draw out what's going on here. So we have one ball that's -6. It was brought into contact with a neutral ball. They're touched together. So -6 plus 0 divided by 2 is going to give us -3. So after that, both balls were -3. Okay. And then a second uncharged pith ball. So it was brought into contact with the second pith ball was brought into contact with the third. So this one was brought into contact, so -3 plus 0 divided by 2 is going to give us -3 and -1.5 and -1.5. Okay. So when the first and third, so this guy and this guy, are brought within 5 centimeters of each other, what's the electrostatic force between them? Okay, now we're ready to use K, Q1, Q2, all over R squared is equal to our electric force or electrostatic force. K is 8.99 times 10 to the 9 newtons meters squared per coulomb squared. Charge 1 is -3, and you have to remember I left it off there, but it's microcoulombs, so times 10 to the -6 coulombs. This one is, I'm going to leave the negative off there. I'll explain why in a sec. 1.5 times 10 to the -6 coulombs, because it's microcoulombs. And then it says that they're separated by a distance of 5 centimeters, so centa is times 10 to the -2 meters. And we have to square it. So we plug that all into our calculator. And you can remember, we can program numbers into our calculator. So I'll program K into my calculator. So the way that I would program that in there is I would go 8.99 times 10 to the 9, and I want to store that as alpha K. And now that's programmed in there. So when I type it in, I can just go alpha K times 3 times 10 to the -6 times 1.5 times 10 to the -6, and then divide that by 5 times 10 to the -2 squared. When I do that, I get my force is, I have 2 sig digs, so I get 16 newtons. So I want to talk about why I left out positive and negative. When we put positive and negative in this answer, it means to the left or to the right, right? It indicates direction. If we put positive and negative in here, it indicates charge. But I know if I have two negative charges that they're going to repel. So this one will go to the left, this one will go to the right. It's a 60 Newton repulsive force, right? This one will go to the right, this one will go to the left. So we use our knowledge of how charges interact with each other to give our direction. We always put it in as positive. We never put the negative in there because it won't give us the right direction. So that's why I have this extra little point here at the bottom. Positive and minus refers to direction the charge will move, not the charge on the object. So it's not correct to put the charge in there. So which is stronger, FE or FG? Take a pick. What do you think? You're on team FE, you're on team FG. Well, we need to compare two things that are kind of similar. So an electron and a proton both have a charge. Good. So they'd have an electrostatic force. The electron orbits around the proton at a certain distance. They both have mass, so they'd have a gravitational force. So what we can do is we can calculate the gravitational force and electric force and compare, well, which one's going to be bigger, which one is going to be smaller, and let's take a look. So let's calculate the electrostatic force. Let's calculate Fe equals K, Q1, Q2, all over R squared. So 8.99 times 10 to the 9 newtons meters squared per Coulomb squared is our constant. The charges are the same, so I can just say Q squared. They both have a charge of the elementary charge, which is 1.6 times 10 to the negative 19 coulombs. So I square that, and they're separated by a distance of 1.59 times 10 to the negative 10 meters. And I have to remember to square that. So I can find out my electrostatic force. So I'll go alpha K. Oops, let me put that in brackets. Alpha K times 1.6 times 10 to the negative 19 squared divided by 1.59 times 10 to the negative 10 squared. So I get a super small force. So this one is 9.1 times 10 to the negative 9 newtons. So gravitational force has got to be bigger. So let's calculate that. So we're going to use Fg equals G m1 m2 all over R squared. And let's do it down here. So 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. The masses are different, so I need to put them both down. So remember that the masses are both in our data book. If I open up our data book here, you have the charge and the mass of protons and electrons. Okay, so those are them there. So that's where I'm getting them from. So 9.11 times 10 to the negative 31 kilograms is an electron, and 1.67 times 10 to the negative 27 kilograms is a proton, and they're all separated by 1.59 times 10 to the negative 10 meters squared. So if I plug that one in, alpha G times 9.11 times 10 to the negative 31 times 1.67 times 10 to the negative 27, and I divide it by 1.59 times 10 to the negative 10 squared. I end up getting, oh, really small number. Oh man, really, really small number. This is way bigger than this. How much bigger? If I divide this by this, oh my God, 2 times 10 to the 39 times bigger. It's way bigger. The gravitational force is negligible. It's so tiny compared to this that it doesn't even matter. And why do you ask? Well, this is 10 to the positive 9, and this is 10 to the negative 11, right? There's no comparison. This starts off 10 to the 20 bigger. So, yeah, electrostatic force is always going to be way, way bigger. When we do some of our diagrams, you'll find that we don't actually include gravity in a lot of them because when they're elementary particles like that, protons, electrons, gravity's nothing. So let's do a couple board questions. I want you guys to try them. Calculate the magnitude of the initial acceleration between 2-point charges, right, of mass 3.3 times 10 to the negative 7. Those are the two charges when they're 4.5 centimeters apart. Okay. So I want you to try this. Before you watch me do it, pause the video. Okay, so we have two charges. Positive 4 microcoulombs and positive 3 microcoulombs, right? So we just found out that gravity is like next to nothing with these two tiny charges, especially one that's times 10 to the negative 7, even that's like super tiny. So the electric force is going to be way, way bigger, right? This is going to be super tiny. The force of gravity, we can leave it off. So we can use Fe equals Q1, Q2, all over R squared. So we would go 8.99 times 10 to the 9 newtons meters squared per coulomb squared. This is 4 times 10 to the negative 6 coulombs. This is 3 times 10 to the negative 6 coulombs micro. And then they are 4.5 times 10 to the negative 2 meters away. Okay, so let's get an answer for that. Oops. Let's do alpha k times 4 times 10 to the negative 6 times 3 times 10 to the negative 6 divided by 4.5 times 10 to the negative 2 squared. So we get 53.27. So although they have different charges, right, the force is going to be the same. So this is 53.27, 53.27, and this is a free body diagram. So F net is just going to equal that Fe. Break this down into Ma. So if I move my mass down below like that, it's just our Fe divided by our mass. So because they have the same mass, they have the same force, then the acceleration is going to be the same between them. All I have to do is I have to take my answer and I have to divide it by the mass of 3.3 times 10 to the negative 7. So they're going to have a huge acceleration, right? And that makes sense. They don't weigh much. So my acceleration is going to be equal to 1.61 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters per second squared. It just wanted magnitude because one is to the left and one is to the right. And that's how you do that question. Let's try another board question. Two-point charges produce an electrostatic force of attraction Fe. Determine the change in electrostatic force produced if both charges were doubled and the distance between them is tripled. Okay, so this is a numbers without numbers question. So leave some space in between. Fe equals K, Q1, Q2, all over R squared. And I like to use a different color. So it says that both charges were doubled, and this is tripled, and because R is squared, this gets squared. So 4 over 9. So this is going to be 4 over 9 of what it was before. So our last two examples we did in Physics 20. Okay, we have charge A, B, and C are -3, +3, and -4. Find the force acting on sphere B. So we did these with gravitational force. We need to do the same thing with electric force. It's the exact same idea, just slightly different formula. So first thing we need to do that's really important is we need to draw a free body diagram. Okay, so we want to find the forces acting on B. So B is going to be attracted to A. So the force, there we go, the force of A is going to be towards it, right? B is also going to be attracted to C, but C is much further away. Although it's got a bigger charge, it's going to be much further away. So it's going to be a much smaller force. So this is a force of C. Okay. We can calculate the force of A and the force of C. We can use our Fe equals K, Q1, Q2, all over R squared. So the first two have the same charge. So 3 times 10 to the negative 6 coulombs. So this is for A. They have the same charge, and they are 20 times 10 to the negative 2 meters apart. Okay, for B, one of them's 3, and one of them's 4, and they are much further apart at 40 centimeters. So we can calculate both of those. So let's plug those into our calculator. So alpha K times 3 times 10 to the negative 6 times 3 times 10 to the negative 6. I'm typing it in like this for a reason. And they are 20 times 10 to the negative 2 meters away. Don't forget to square it. So this is A. And then for B, I can just push second enter. And the only difference is they are 40 centimeters apart. And one of them has a charge of 4. So you can see that it's much further. It's about a quarter of the other one. Okay, so those are our two values. So let's go back to this screen here. And we can write down those values. So this one is 2.02. And this is 0.6, what was it, 67. Obviously, I'm going to use the full numbers. Well, now it's just an FNet equation, right? FNet, I'm going to make this way positive, this way negative, is just equal to force applied. Sorry, FA minus FB. It's not force applied, it's force of A and force of B. So I'll just take this minus this. So if I go on my calculator and I take this minus this, I get my answer. That's it. 1.34. 2 sig digs actually, so 1.2 newtons, it's positive, so it's going to be to the left. So that's our answer. So our last question is the same thing, but it's more of an RCS chart question. We have 3 point charges, each having identical charge of +2, are aligned below. Determine the initial net force acting on charge B due to charge A and C. So same idea. So all 3 charges are positive. So this is important because people who get this wrong don't start with a free body diagram. Okay? Remember that A and B are going to be repelled from each other. So B is going to be repelled from A. So this is the force of A in this situation. It's a repulsive force. And C is also going to repel B like that. So this is force of C in this situation, right? I should draw, let me fix that. I should draw C should be a little bit smaller because it's further away. So I'm going to draw it a little bit smaller. So this is what it's going to look like. So if we draw a tip to tail, right, this is B. Oops. This is C. Sorry about that. I don't know why it jumps around so much. So this is our net force. That doesn't make a right angle triangle. So what we need is we need an RCS chart. So that's what we're going to do, is we're going to build an RCS chart. This is A, this is B, this is our total, this is X, and this is Y. Okay, so what we need to do is we need to figure out our angles. So let's do our angles first. Let's look at our original picture. So A is to the right. Well, that's easy in RCS. This is 0, 90, 180, 270. So if we're to the right, it's going to be 0 degrees. And then this one is a little bit tricky, but from the horizontal to this is 40 degrees. So from the horizontal to this is 40 degrees, right? So it's going to be 180 with 40 less than that. So 180 minus 40 is going to be 140. So this is going to be 140 degrees. And we need a magnitude, so I'm just going to calculate that really quick. I'm just going to use, oops. There we go, I'm just going to use this. So in this question, we use, all of them are 2 microcoulombs, and they are, one of them is 5 centimeters apart. So get rid of that. So this is the one that's 5 centimeters apart, which is A. So this is 14.384. And then the only difference between the other ones is that they are 7 centimeters apart. So this is 7.338. Okay, so to do this in our RCS chart, it's 14.358 cos of 0, 7.338 cos of 140, y is sine, oops. Okay, so I'll plug that into my calculator. So I'll just take the full answer. So I'll do this, cos of 0, and then I'll do this, cos of 140. So my total x is 8.76 newtons. And then I'll go second enter, switch all my coses to sines. And then this is 4.71. So if we draw our final triangle, right, our x is positive, so we go up, and our y, oh sorry, that's y. Our y is positive and we go up, and our x is positive, so we go to the right. So this is 4.71, this is 8.76. These are all newtons, like that. So if we find the hypotenuse, and then we tan -1, opposite over adjacent, and then the angle's going to be, so this is northeast, so we're not going directly north, we're going east of north. Whatever our angle is, it's going to be east of north. So let's finish this off in our calculator. So we're going to take this squared plus, oops, plus this squared, square root it, and that's our magnitude. So our magnitude is, we have 2 sig digs So 10 newtons would be 2 sig digs. And then we're going to tan -1 opposite over adjacent. And we get 62 degrees east of north. And then that's our final answer. That'd be the net force acting on it. There we go. So this is our homework. It's got some of the 2D stuff. Make sure you try that. Just regular Coulombs Law, 1D and then 2D. So